All right, we're going to start on chapter 8 today. Start with a misleading stat. This was at the presidential debate between then President Obama and Governor Mitt Romney. Questioner said that women make only 72 cents for every dollar that men make. Both Obama and Mitt Romney agreed. This is a misleading statistic. Not that there aren't specific cases where women do make less for doing the same thing, and we'll talk about that in a second. But this is a misleading statistic just in the way it's stated because there are other things going on behind the scenes. As I mentioned here, women do earn different amounts than men, unfortunately, in a couple of different areas. Women in the WNBA as compared to men in the National Basketball Association. Women Olympic soccer is a glaring example of them being paid less for doing the same, and literally more because they are much more successful than the men. Women leading actors versus men in movies happens all the time, but there's something else going on behind the scene. And that is employees who work longer hours tend to make more money. Census report does not talk about that. It doesn't say anything about women and men being at the same level of job. The key is right here. Women are also more likely to spend time outside of the labor force caring for children, okay? When economists control for such factors, they find that the gender gap more or less disappears. Here was a 2009 study done by the Department of Labor. In 2005, June O'Neill, the former director of the Congressional Budget Office, found exactly the same thing as this study. There is no gender gap in wages among men and women with similar family roles. It's different choices, okay? Many times women choose to spend the time at home and raise a child. It's a wonderful choice, but it results in a wage inequality. And I just did a quick example. Two people started working in 1980, $40,000 a year. They each worked until 2010. They worked for 30 years, but Ann took 7 years off to raise her family. Look at the amount of income inequality, okay? Ann earned 77% of what Albert earned. Oh yes, sometimes we just lose confidence in what we hear when it comes to statistics. And speaking of confidence, that's where we are headed in chapter 8. We're going to be talking about confidence intervals. How confident are we for the statistics that we're going to be working with? Okay, so consider, this is data with teens and their weekly allowance, the amount of money they earn. I think there's 15 of these here. 15, if you were to add those all up and divide by 15, I've done that, and you get $11.45. So X bar is $11.45, okay? We know the standard deviation in this study is $4.59, okay? What we want to do is say what would be a reasonable estimate for the population weekly allowance of all teens, okay? The 1145 is just for this particular group, okay? So 1145 is just for that group. Can we say that 1145 is a reasonable approximation for the entire population of teenagers? And if we do say that, how confident are we that it is a reasonable approximation for mu? And that is the start of confidence intervals. Okay, so there is the range of data. Once again, I just repeated it, same thing, standard deviation. And we know that 1145 is the mean by adding them up and divide by 15. We want to be 95.44% confident. bell-shaped curve. 1145 is here. 95.44 should jump out at you, ring a bell, right? Isn't it 2 standard deviations? Okay. Now, we want to be 95.44% certain that our range will contain the actual population mean. With only 15 scores, we should have some sort of sense of normalcy on this. Is it really a bell-shaped curve? With only 15 scores, technically, we should do a probability plot, see if it lines up in a straight line, okay? We are going to assume that this data is normally distributed, okay? And therefore, let's proceed with the problem. If you want to be 2 standard deviations above and below, we learned in chapter 7, 2 standard deviations above and below when you're dealing with a sample and a sample mean. You've got to take this for the X bar. You've got to take the standard deviation and divide by the square root of 15, okay? So if you want to go 2 standard deviations above and below, I'm going to take 4.59. I'm going to divide by the square root of 15. I'm going to get 1.19, okay? So 1.19 is going to be the standard deviation, and I want 2 of these. So I want 2 times the 4.59 over root 15, which is 2 times 1.19, and I get 2.37. I want to go 2.37 above. I want to go 2.37 below, okay? So if I take 1145 and add 2.37, I get 13.82. If I take 1145 and subtract 2.37, I get 9.08. Okay? This is called a 95.44% confidence interval. In other words, we are 95.44% confident that the actual population mean will be in this range. Does it have to be? No. There's a small percentage of chance that it would not be. Okay? But let's once again review how we did this. 95.44 is this area. 4.9544. That's that area. Okay? What is left out here? What is left? 1 minus 0.9544 is 0.0456 for alpha. That's the area we don't want. Divided by 2 is 0.0228. And here's the beautiful thing. If you do a reverse lookup on your Z-chart, okay, do a reverse lookup of 0.0228. 0.0228 is exactly -2. The z-value here is -2 and +2. Okay? So what you end up doing to find what you add and subtract to the mean, you take the z-value times the standard deviation. If you forget everything else I said this morning or today, whenever you're viewing this, if you forget everything else, how you find what you add and subtract on to the mean is the z-value times the standard deviation. Write that down someplace. Z-value times the standard deviation. All right. So, just a couple questions here. Are we guaranteed that population mean will be in that range? No, we're not guaranteed, but we're 95.44% confident it is. Would another group of 15 weekly allowance give us the same range? No, but it should be reasonably close. All right. Okay, so here are 36 randomly selected millionaires in the United States. I think we did a problem earlier with this same data, okay? We assume the standard deviation is 13, so the standard deviation for this population is 13. We know 21.07 is the total of that. Thank goodness I don't have to add those all up. And there are 36 of them. So if I take 2107 divided by 36, I get that X bar is 58.52. Okay? We want to determine a 68.26% confidence interval for the mean age of all millionaires. Okay? All right, so here we go. Bell-shaped curve. Do we have to worry about being bell-shaped, being normal? No, there's 36. We're in great shape. Okay? We know that we have 58.52 here. Okay? Sorry, that should be 53. I did not round off correctly. 58.53. All right, and this should jump out at you. Is that not one standard deviation on either side? Okay, and remember what I just said a little bit ago. To find out how much you add on and subtract off, you take the z-value, the 1, 68.26 in the middle is going to have z-values of plus or minus 1. It's one standard deviation on either side. So I've got to take one of these. So 1 times 13 over square root of 36. Square root of 36 is 6. 6 into 13, I think, is 2.17. Check that. 2.17, yeah. So I've got to add 2.17 and subtract to this. So 58.53 plus 2.17 is 60.7. 58.53 minus 2.17 is 56.36. Okay? There's our interval. We are 68.26% confident that the actual mean age of all U.S. millionaires is going to be in that range. Okay? Will the mean of our sample equal the population mean? Probably not, but it should be reasonably close. Okay? Determine a 99.74% confidence interval. Same data. Okay? Okay, instead of 1 for 99.74, hopefully you recall it is 3. All right? And once again, if you do the 99.74 in the middle, if you find the area that's left, let's just do it. 1 minus 0.9974 gives me an alpha of 0.0026. That's for both ends. Divide by 2 is 0.0013. The area down here is 0.0013. Do a reverse lookup on 0.0013 and you get -3. -3 for Z and +3. So you want to go 3 standard deviations on either side. So I'll take 3 times 2.17. I get 6.51. I'm going to add it to 58.53. I get 65.04. I'm going to take 3 times 2.17 and subtract it from 58.53, and I'm going to get 52.02. Okay? There's our 99.74% confidence interval. We are 99.74% confident that the actual population mean age of millionaires is in that range. Okay? Can we be certain that any set of 36 randomly selected ages will have all 36 ages within this range? No. Once again, if we are 99.74% that the actual population mean is in there, but there may be some small errors. It's not foolproof. Okay. Study is done establishing a 95.44% confidence interval of this for the population mean. Assuming the population standard deviation was 13.36, And normal, can you establish the sample mean and the number of data in the sample? Okay, so there's a lot going on here. Let's talk about this. 95.44 is 2 standard deviations on either side, okay? Now, let's find X bar. X bar has got to be dead in the middle of those two because we've added and subtracted, right? So let's define what's the middle. So we're going to take 75.19 plus 84.63, okay? And then divide that answer by 2, and we get 79.91 is X bar. Okay? All right, so 79.91 is dead in the middle. The standard deviation is 13.36. It's normal. Can we find the sample mean? Yes, we just did that, 79.91. And the number of data in the sample. Now, we know that to go from this to our range, we added and subtracted something to that, didn't we? We added and subtracted to get the confidence interval. Well, what did we add and subtract? It was a z-value of 2. We want 2 standard deviations, so we know that 2 times the standard deviation of 13.36 over the square root of how many people were surveyed, the square root of the number of data in the sample. This is what we added and subtracted on. Well, what did we add and subtract to this to get that? Well, I don't care. You can take either one of those and subtract this. So 84.63 minus 79.91 is, I get 4.72. So I must have added 4.72 onto this and subtracted 4.72 onto this to get this range. This then, right here, is 4.72. Okay? How do we find the number of data? We need to solve for n. So multiply the root n over to here, put it over here. So I'm going to take 2 times 13.36, get that answer, divide by 4.72. Okay, let me try that again. Let's multiply both sides by root n. 4.72 root n equals 2 times 13.36. All right? All right, let's solve for this dang thing. 13.36 times 2 equals, divided by 4.72 equals, I get the square root of n is 5.66. How do I find n? Get rid of a root? We have to square both sides. So let's square that, and I get 32 people. Okay? All right, so going on, try another problem. A study has a 68.26% confidence interval of 55.12 to 67.34 for samples of an unknown number of data, and we're assuming normal. Find the sample mean, the number of data, just like the last one. So it's a repeat of the last one. Let's go through it. 68.26 we should know is 1 standard deviation on either side. Okay, so instead of a 2, we're going to have a 1 right here. And then we're going to do the same thing as we did in the last one. To find X bar, you have to find the number in the middle. So I'm going to add those two guys, 55.12 plus 67.34 equals, divided by 2, 61.23 is dead in the middle. So X bar is 61.23. Okay? Now, what do I add and subtract onto that to get this range? Okay, so I'm going to subtract 55.12 from that middle. So I know that what I add and subtract on is 6.11 is equal to 1 standard deviation times 1 standard deviation. So I have, just like in this one over here where we had 2, we have a standard deviation is 25.4 sorry, I'm a little close to the other one, divided by the square root of n, just like that. Multiply both sides, 6.11 root n is 25.4. So to solve, I take 25.4 divided by 6.11, and I get square root of n is 4.16. And how do you solve it? You square it to get rid of the root. And I get that there had to be 17 people in the study. Okay, homework. There you see there are 2 problems on that screen. There are, and where did that come from? There are 3 problems on that screen, and then some book problems down at the bottom, and hopefully you will find section 1 here to be extremely easy. Good luck.